Okay, this is the video for 5.1, Fundamental Identities. We've already gone over these identities before. Now we're going to use them to rewrite trig functions in terms of other trig functions. And in the next section, we'll use these to prove trig identities. So there we go. I crossed out the negative angle identities just because we're not going to really use those. So we're just interested in the reciprocal identities, the quotient identities, and the Pythagorean identities. Okay. It's been a while, so I guess I'll reiterate this. The Pythagorean identities, you should be comfortable. You need to be able to recognize these in all their different forms. So we talked about how to get from sine squared plus cosine squared equals 1 to these other two forms right here. The tangent squared plus 1 equals secant squared, and the 1 plus cotangent squared equals cosecant squared. Those are found just by dividing by sine squared, which is what we did in this first one. I took the regular Pythagorean identity and divided it by sine squared. Sorry, divided it by cosine squared to get this. Divided it by sine squared to get this over here. But each one of those you could solve for any one of the variables. Like right now, the first one solved for 1. I could solve it in terms of sine. I could solve it for sine, or I could solve it for cosine just by moving the other trig function. Same thing for these other two, and we'll do some of those in this section. Okay. So first we're going to talk about writing one trig function in terms of another. There's no like perfect way, there's no like one size fits all algorithm I can teach you. I'll just go through what I do. I would look at the identity. So if we're asked to write one trig function in terms of the other, I'm going to look at all the identities and find the identities that involve my first trig function, and do the same thing to list all the identities that involve my second function, my second trig function, and then look for some link between those two. So this doesn't really make sense until you see an example. So here's our example. Write cosine in terms of tangent. So what I've done is I've listed all the different identities that involve cosine. So this first one, secant equals 1 over cosine, tangent equals sine over cosine, and so on. Every identity on my list that involved cosine I listed here. On the right, I did the same thing for tangent. I listed any identity that involves tangent. Okay. So that's steps 1 and 2. Step 3, find a way to link the two together. Well, I've identified these two formulas here, these two identities that involve cosine and tangent, the two that I'm trying to link. And then for their other function, they both involve secant, and that's what I'm really looking for here. That allows me, if I can solve these things for secant, I can I can use that to rewrite this cosine in terms of secant, and then secant in terms of tangent. So it's like we're using secant as a bridge to get from cosine to tangent. That's kind of our link between the two. So I'm going to walk you through how I do that. So here again are the two functions, the two identities, just rewritten. Sometimes you're not this lucky. In this section, it should mainly just be one step like this. In the future sections, you may have to jump through a couple of these links before you get to where you want to go. And that's actually more realistic, especially in higher mathematics when you're trying to simplify a kind of complicated trig expression. You may have to jump through a few hoops to get a nice simplified version. Okay. So first, since I'm trying to write cosine, what I'm trying to get, I want to get cosine by itself on one side of my equation, and then everything else on the other. And so what I did is I solved this first identity for cosine. And hopefully you've done this enough, or actually we've got this identity written. You know, early on in the semester, I just told you need to kind of be comfortable changing these out. If secant is equal to 1 over cosine, then cosine is equal to 1 over secant. But if you want to walk through the algebra that gets you there, I've got that written. So starting from secant equals 1 over cosine. If I multiply by cosine on both sides, like I've done here in the blue, then I can cancel my cosines here on the right. I've got 1 on top, 1 on bottom. On my fraction, I can cancel those out. So now I've got secant times cosine equals 1. And now I can divide that by secant to solve for cosine. So divide by secant, that allows me to cancel the secant on the left. On the right, I have 1 over secant. So that may be a lot of work. It may look like a lot of work, but this is something that you may have just memorized earlier on. Okay, but it's just a couple of algebraic operations there. Okay, so why did I do that? Well, now, since we're trying to write cosine in terms of tangent, now on the left I'm going to have cosine equals, and then I'm going to rewrite this 1 over secant as something involving tangent. And then I'll be able to say, okay, cosine is now written in terms of tangent. So what do I do next? Since I've got this thing, I've got this expression involving secant, if I can solve my other identity for secant, I can plug that in. Secant has to equal this. I've already got it done here, so I'll just say it. I can say this secant here, down in the denominator of my fraction, equals plus or minus tangent squared theta plus 1. So when I plug that in right there, now I've got cosine in terms of just tangent. So how did I do that? I took my second version of the Pythagorean identity, and I solved it for secant. And there's just one step there. I take the square root of both sides. But you have to remember that when you take the square root of a variable, that gives you two solutions, the positive or negative square root. Okay, so my secant equals plus or minus tangent squared theta plus 1. I then just substitute that in. So we've got cosine equals that. I've got the denominator rationalized here. Again, that's not something I'm hugely invested in you knowing how to do, but there's not a lot to it. I multiply the top and the bottom by that square root. On top, I just have 1 times that square root. It leaves me that square root. On bottom, the square roots cancel. So rationalizing the denominators, not a big deal. Here it is written out with, a little less complicated, in a little less complicated form. If we multiply the top and bottom by the square root, on the bottom we end up with square root of b squared, which simplifies to just b. Again, that just cancels out our radical. That's what I mean by rationalizing this denominator, getting rid of the radical from the denominator. Okay. All right, one other example. I actually am going to cut out of this and film this on my board so I can write it out. This is one of the best methods, I would say, for simplifying trig functions, for rewriting trig functions, for proving identities. You've got a lot of these in your homework. So a lot of times you can get by just by rewriting your expressions in terms of sine and cosine. So if we go back up, up to the problem we were trying to deal with, we could rewrite everything in terms of sine and cosine. That would have also been an option here. Okay. But that's one of my favorite ways of simplifying these things. When I am doing this, when I'm trying to solve an integral, it's got a complicated trig function in it. A lot of times this is my first step. So when I learned trig, this is one of the things that really stuck with me. I think it's easy to remember. It's just a great tool, so I thought I'd kind of emphasize it and make a separate video for that. So that's it. I'll go ahead and cut this off, and then you can watch that video.